Welcome to What the Physics is Behind Car Crashes. On today's show, we will cover the energy involved in a car crash and safety mechanism.
So, how do cars run? Energy transformation occurs in cars. Gasoline's chemical energy turns into kinetic energy. 5 teaspoons of gas can accelerate a car to 65 kilometers per hour. The internal combustion engine in the car converts the chemical energy in gasoline and oxygen into thermal energy, which transforms into kinetic energy. The car gains velocity because of its gain in kinetic energy, causing it to move.
If the car wants to stop, then its kinetic energy has to go somewhere. If the brakes do the stopping, energy is dissipated by the brakes heating up. The car's kinetic energy is lost through friction, which is converted to heat energy. If the brakes are not the ones doing the stopping, then it's a collision. Without the brakes, the car's kinetic energy is maintained until the point of a collision. In a collision, some energy is dissipated through the crumpling and bending of the metal in the outer regions of the car.
But what happens to the driver? Well, Sir Isaac Newton will help us explain. When the car moves, the apple rolls off.
Wait, why does the apple roll off without moving with the car?
Well, let's replay that. Although the car was moving, the apple is at rest and will remain at rest and resist the surrounding change of motion. This is the law of inertia.
Similarly, this guy driving the car will stay in motion at original speed, even though the car will crash into the stop sign and come to a stop, until he strikes the steering wheel of the windshield. On a similar concept, Newton's second law, F equals ma, explains that the object will accelerate in the direction of the force. If we manipulate this formula by multiplying the other side with delta t, we have F delta t equals m delta v. The force applied over a period of time is impulse, which is the change in momentum.
In the case of car crashes, a bigger force applied over a shorter period of time is not as ideal as a smaller force applied over a longer period of time. We can apply this theory to an egg drop demonstration. This is egg number 1 and this is egg number 2. Egg number 1 had an unfortunate accident. Upon impact, it experienced a large force in a very short amount of time. Bye-bye egg number 1. Egg number 2 witnessed the death of egg number 1 and became depressed.
I'm depressed! Oh, but I was saved by the blanket!
Number 2 did not fall to her death due to the flexible barrier. It experienced a smaller force over a longer period of time.
Yay!
Egg number 2 lives!
Before we start this clip, we would like to excuse the hairs exposed in the video. No, I am not going bald. Moving on, there are several designs to the car based on this principle, used to decrease the effect of collisions on soft human internal organs, including the seatbelt, airbag, and the frontal criminal zone of cars. Let's hit replay.
See how all of these designs ensured that the driver was not carried away on a stretcher, but was able to instead walk away from the crash scene.
Yay!
The effect of collision on the soft human internal organs were decreased due to these safety mechanisms.
First of all, cars are designed with a pair of steel rails connecting the front bumper to the body. These are designed to crumple, bend, and deform to absorb the crash forces. The duration of the impact is therefore lengthened so the guy can experience a deceleration over a longer period of time, therefore a smaller impulse.
If this front zone of cars was rigid, the stopping would be abrupt and passengers would experience a big deceleration over a very short period of time, or a huge impulse.
Next, seatbelts. They are required to be worn by law for a reason. They ensure that the person will slow down with the occupant compartment and not crash into the steering wheel or the windshield. In other words, the guy's momentum will be absorbed by the car rather than the dashboard or the pavement.
Airbags also employed the idea of impulse. They're a soft barrier between the driver and windshield, which applies a small force to the head of the driver over a long period of time. Another equation is also important in the design of airbags. Pressure equals force over area. As aforementioned, airbags apply a small force on the passengers. This is possible due to its large surface area. It distributes the force over a person's body to minimize the injury sustained.
If the airbag was as small as a nail, the force applied over a tiny surface area would create a large pressure, defeating the purpose of the airbag.
When the driver crashes into the nail.
Ow!
When the driver crashes into the large airbag.
Whee! Cars bigger in size and weight will also have an advantage during a collision. This is based on the law of conservation of momentum. If identical cars traveling at the same speed collide head-on, their momentums cancel each other. Occupants of each car would experience the same change in momentum from the speed they were traveling at to 0.
However, if two cars of unequal mass collide, the car with a bigger mass would drive the car with less mass backwards, causing a greater change in momentum in the lighter car. The passengers of that car would therefore experience bigger forces, so lighter, smaller cars aren't as protective as bigger, heavier cars. Despite all these safety mechanisms within vehicles,
we still advise you to be cautious on the road and drive bigger cars.
You don't want to end up like egg number 1.
Woo!